Hello, my name is JoshuaPaulBarnard, and I will be presenting on my project of comparing linear regression with K nearest neighbors, decision tree, and random forest machine learning methods using Bayesian Inference to predict wine quality using Python. So, what is wine quality? Well, wine quality is not a precise measure. It is very objective. It is usually considered to be composed of extrinsic and intrinsic properties. Here we will be focusing on the objective physiochemical properties which make up wine and how it affects the quality. Why would we want to do this? Well, all wineries are businesses, and as businesses they need to know how to market their wines and how to do proper quality control. So these models can help a winery manage their operations much smoother. The data comes from Paulo Cortes in Portugal. Is from the Vinho Verde product line in the Minho region of northwest Portugal. Their wines are typically medium in alcohol and are usually pretty fresh. Our data came in two separate data sets, and one for white wines and one for red wines. They have both been stated as CSVs. Well, that is supposed to mean comma separated variable, but this time they were semicolons, so we had to deal with that. But we got it all together and combined the two data sets to make to have a total amount of samples of over 6,000. We then created three new variables. One was a wine type, which is a string categorical variable, and then we created what are called indicator variables. So under red wine, it only has 0 and 1. 1 meaning it's a red wine, and 0 meaning it's not. And so we did that for both red wine and white wine. This allows us to do regressions. We tried many different transformations. There were the biggest issues with residuals were with quality and alcohol. There were some issues with normality for other variables. So we tried transformations on around 6 of our variables. All these transformations here, log, power, root, inverse, reciprocal, and standardization were all tried on quality. None helped. Most of them made things worse, actually. So then we loaded up our data into a SQL database, and this is a schema that you can see for it. These are the variable names. So now that we're starting to look into the data, we need to know what our variables are about. Well, quality is actually a median score from at least 3 evaluations made by wine experts, from 0 to 10, meaning very bad to very excellent. We don't know where these experts are from, but we're assuming Portugal, and it could be more than 3 evaluations, but it's at least 3. So there's some variability in there. Wine type is the variable that we created. Fixed acidity refers to tartaric acid in this case. Citric acid refers to citric acid. But in winemaking, there's 3 primary acids. The third one is malic acid, and that is not accounted for here, so that could be a confounding variable. Volatile acidity is bad. That is vinegar. You do not want VA, and so it denotes spoilage. So you always want to keep VA low. And residual sugar is glucose and fructose. Some people like dry wine, some people like sweet wines. That's a personal preference, but the more sugar you start with, the more alcohol you can produce, as yeast consumes sugar to produce alcohol. Chloride refers to sodium chloride, which is salt. People don't like salty wines, at least usually, so people usually don't like that in their wines. Free sulfur dioxide helps keep your wine clean and fresh. It's not noticeable in low amounts, but if there's too much, it imparts a chemically flavor and aroma to a wine. Total sulfur dioxide is the total amount of free and bound CO2. So there can be some multicollinearity between it and the free SO2. Sulfates are potassium sulfate. They're additive, which helps raise CO2 levels. Density, usually wine is the same density as water, and we don't like thick wines usually. They're syrupy. pH is a logarithmic scale from 0 to 14, 0 being very acidic. Water is 7. For comparison, most wines are acidic, with whites usually being more acidic. And percent of alcohol, this helps bring out aromas and taste in the wine. So if there's a lot of faults, it's going to be more noticeable, while in a good quality wine with no faults, it will help bring out those good attributes. So we created what's called a causal loop diagram. You can see as pH affects free SO2, so you can see a negative correlation there. Thick wines are bad, so a negative correlation. People usually like fixed acidity, so there's a positive correlation there. So this allows us to start to visualize how we can put together a model. So then we just look at the data to see if there's any values that are too high or too low. Everything seems to be within reason. There could be outliers, but not unrealistic outliers. So then we look at our variables themselves, and we see that alcohol, density, chlorides, and volatile acidity are the highest correlated variables to quality. These all make sense. The lowest correlated ones are total sulfur dioxide, pH, sulfates, and residual sugar. Particularly the total sulfur dioxide was expected. Sulfates apparently don't impart too much of a flavor. They don't correlate too much with much. So then we checked for multicollinearity based on our domain knowledge. We checked total sulfur dioxide with sulfates and free sulfur dioxide. There was a high correlation between free sulfur dioxide and total sulfur dioxide. Other than that, we had a strong correlation between density and alcohol, as alcohol is the only chemical compound in wine that has a negative, that has a density less than water, and density and residual sugar, as typically alcohol and residual sugar are the two main factors that affect the density of your wine. A lot of sugar, it gets very thick. So these all make sense, and so we kept every variable in our analysis. We didn't want to make our models too fragile. So then we checked for outliers, which was using the interquartile ranges. There were a lot of potential outliers. We went through them, and we decided that it's best to keep them. As we mentioned earlier, the variables are all within the proper range, so we don't want to make our model too fragile. So we start modeling it. We start with the null model. We're going to use a standard deviation here as error. So we start with an error of 0.87. Now we go on to linear regression, and that's the general formula for linear regression. And bootstrapping is where we resample our data. This can help us also satisfy the assumptions for ordinary least squares regression, and then there's n-fold cross validation, which allows us to break our data set into pieces and analyze it against each other. Our best models based on domain knowledge were the Olin, the simplest, and the interactions. The interactions is based off of that causal loop diagram I showed before. When we compare our models, we see that the interactions had the lowest error and the highest coefficient of determination, but we decided to keep the Olin model as the beta coefficients matched our causal loop diagram. Now, we're going to move on to K nearest neighbors regression, and that refers to finding a point in between the classes that can be used for regression and classification. We checked to see how many folds we should use. We tried one. There were some issues with convergence and high variance of the model. We then performed cross-fold, 10-fold cross-validation 3 times to help us understand the model and how it generalizes. And we got a significantly lower error and a larger coefficient of determination compared to our previous models. So we tried now decision tree. Decision tree breaks their data set up into branches. They just kind of traverse down. You have nodes, and it can also handle categorical and numerical variables. We found 4. A tree depth of 4 was the best. There were some issues with high bias with our model, and so now we performed cross-fold validation with decision tree as well, and it had higher error and a lower coefficient. We tried random tree. Random tree is very similar to decision tree. A random forest is very similar to decision tree. But it helps to not overfit as much. We chose 15 trees, and this also suffers from high variance. After all was done, the error was around that of our linear regression model, and yeah. So then we compare all of them together, and we can see that K nearest neighbors did the best in this situation, both for error and the coefficient of determination. We then examined the posterior distributions of each and got the probability of how likely one is better than the other. And in the end, only decision tree was worse than linear regression, and K nearest neighbor was better than all the others. So our final model is the all-in model using K nearest neighbors regression. We did some predictions with this, and we can see that we did a red wine with moderate alcohol content, low sugar. We got a pretty good score of 7. That was expected. But then we did a low white wine with a lot of sulfur dioxide and a high alcohol content, very sweet, and that got a lower score than expected, a 5. And then we tried a faulty wine, a lot of volatile acidity and salty, a lot of chlorides and potassium sulfate, and that got a higher score than expected. So that was interesting. So this model is limited. You can't. I mean, all the data is from northwest Portugal, so and all from the same winery. So it hasn't been proven to really be generalizable to other wines and wineries, and that should be taken into consideration before using. And in general, we can see that linear regression performed better than the null model and decision tree regression, but KNN regression performed better than all of them. The simple and the complex models were not always the best, but sometimes just the normal model can yield the best results. Here are our references, and here's me pouring wine in the Sonoma Napa regions of California. I have experience in the wine industry, and I'm educated in data analysis and data science. Thank you very much, and have a great day. Bye.